Hello everybody, and welcome to our third BrainVision Analyzer 2 webinar for this year. As implied in the topic, today's webinar will be about spectral analysis. You are about to grasp the basics of spectral analysis, mainly focusing on Fast Fourier Transform. Let me first introduce ourselves to you. My name is Kidis Mideksa, and I will be your today's presenter. With me are my colleagues Michael, Bastian, and Laura as moderation team. They will be there for you to assist you in content-related questions or technical difficulties you come across during the webinar. We are all pleased that so many of you have joined us today. So in the next 90 minutes or so, the intended goals are first to get an insight about spectral analysis by diving into the basic concepts of Fourier transform. Next is to familiarize you with the functionalities of the Fast Fourier Transform module implemented in Analyzer 2. Hopefully, by the end of the webinar, you will be highly motivated and encouraged to make use of FFT's functionality as part of your processing pipeline and broaden your research questions beyond time domain analysis. Moreover, you will also learn how to extract and export some relevant information from these frequency domain analysis. Okay, let's move on to the contents for today's session. We will begin by revising the origins of EEG oscillations and the classification of these oscillations into different frequency bands. In the second section, we will focus on FFT and talk about its theoretical basis. Then the third section will be about getting to know its implementation in Analyzer, along with the output options offered in the FFT module. How to extract certain measures from the output of FFT will also be covered. We will also create awareness of certain assumptions and prerequisites that should be done before applying FFT. In this section, we will also open up Analyzer and demonstrate how to use FFT using an experimental data. Then we will have time for open questions. Please feel free to send your questions at any time to the moderation team. Finally, we will close the webinar by providing you the main take-home messages as well as some recommendations for further reading. Okay, so let's go step by step and start with some theoretical background. Remember that EEG oscillations arise from the interplay of many neural ensembles through excitatory and inhibitory synapses. What you see here on the very left is the zoomed version of a single pyramidal cell. These pyramidal cells are usually found spatially aligned in the most superficial layers of the brain, and their activity is synchronous. And that's why they produce the largest signal that can be measured from the scalp. So the postsynaptic potentials of many of these pyramidal neurons that can be modeled as electrical dipoles highly contribute to the signal measured by EEG. So these measured oscillatory activities can have a repetitive pattern, the so-called rhythmic activity, or evolve over time, which is the so-called transients. Moreover, oscillations can be classified as spontaneous, evoked, or induced. Spontaneous means that the activity is completely uncorrelated with the occurrence of an experimental condition. Evoked means that the activity is time-locked and also phase-locked to the onset of an experimental condition, whereas induced means that the activity is not phase-locked but time-locked to the experimental condition. So this rhythmic oscillatory activity driven by the flow of current during the interplay of many neurons can be categorized into different frequency bands. In EEG research, there is a standard nomenclature of frequency bands, which is summarized in this table, from the lowest delta to the highest gamma frequency, or from the slowest to the fastest wave when observed from the morphology perspective. And the definition of their respective frequency range varies from publication to publication. There are also publications that define frequency bands based on the individual alpha frequency of each subject. These brainwaves differ in shape from one individual to another, depending on the functional status of the brain, such as when they are at the relaxed state, or attention, or sleep, or even some neural disorder. So the brain state of the individual makes certain frequencies more dominant. For example, the well-known experimental paradigm used to study spontaneous oscillatory activity is the state of eyes closed at rest. This brain state generates alpha waves, which is typically in the range of 8 to 12 Hz. Okay, now that we have revised some basics, let's move on to the next theoretical background on Fast Fourier Transform, the FFT. We know so far that EEG constitutes a mixture of neural oscillations that can be categorized into different frequency bands. But what is the analysis technique that helps us identify these hidden frequencies? The answer is using spectral analysis. And among the spectral analysis techniques, today's webinar will focus only on FFT. The blue signal represents EEG in time domain that we typically record. And our goal is to use spectral analysis to be able to evaluate the frequency component that constitutes the original signal. So spectral analysis decomposes the original signal into its constituent frequency components. And as you can see, the original signal is composed of 20, 30, and 40 Hz frequency components. So, what is Fourier transform? As you already know, it is the frequency domain representation of a time domain signal. And it also refers to the mathematical operation that translates the time domain to its frequency domain representation. So we will look now briefly at this mathematical operation. Joseph Fourier showed that a signal can be represented as a summation of simple sinusoids, namely sines and cosines. Each of these sinusoids are defined by their frequency, amplitude, and phase. So we have a time domain signal which we can decompose into sines and cosines of various frequencies. Then the next question is, how should we calculate the amplitude at those frequencies? The answer is to use Fourier transform. What it does is, it multiplies the time domain signal x of t by a basis function, which are the sinusoids. This basis function, denoted by the symbol psi, is represented by a complex exponential function, that is, the cosine function representing the real part and the sine function representing the imaginary part. So, substituting this equation for psi, we will get the following expression. And conjugating psi results in replacing the plus sign to a minus sign. And due to the complex sinusoids, the result of the computation will be a complex number per frequency, which are called Fourier coefficients. One can, of course, use these Fourier coefficients to recover back the original time domain signal by using the inverse Fourier transform algorithm. But what does these Fourier coefficients tell us? When we apply Fourier transform on our EEG signal, it will correlate or multiply it with the complex sinusoidal function, once with the cosine function that makes up the real part, and once with the sine function that makes up the imaginary part. Wherever the EEG signal and the sinusoidal function are similar, they will multiply and sum to a large coefficient. And whenever the EEG signal and the sinusoidal function are dissimilar, they will multiply and sum to a small coefficient. Therefore, the Fourier coefficients tells us the measure of similarity between the original EEG signal and the complex sinusoid. Now, how can we make use of these complex Fourier coefficients? Well, we can plot this complex number on a complex plane by using real and imaginary parts of the number as coordinates. Once we plot the points, we can extract its information of magnitude by using Pythagoras theorem and extract its information of phase or angle by using arc-tangent, which tells us how well the frequency components are aligned in time. The magnitude, or the so-called absolute value of the coefficients, correspond to the spectral amplitude or the strength of the frequency component of the signal at a particular frequency bin. And squaring the amplitude value or the absolute value will result in spectral power. Now, let's look at some simple rhythmic oscillations. In this example, we see 4 signals, each with a duration of 1 second. The first 3 sinusoidal waves oscillate at 3 distinct frequencies. If we take a closer look into the first signal, we can count 10 cycles within 1 second. This means that this signal oscillates with a frequency of 10 Hz. Similarly, if we count for the second and third signals, they oscillate with a frequency of 20 and 50 Hz respectively. The last signal corresponds to a linear combination of the first 3 sinusoidal signals. This could be something more similar to what we would expect to see in real EEG signals, where we know that we have a contribution of multiple frequency components. These 4 rhythmic signals are stationary. This means that their spectral properties, which are the amplitude, frequency, and phase, does not change over time. So if we apply FFT to these signals, we will get their corresponding distinctive spectra as shown on the right. In the x-axis, we have frequency in Hertz, and the y-axis shows the spectral amplitude in microvolt. Because the Fourier transform decomposes a signal into a set of sinusoids, we would expect to see a single amplitude value at a single frequency bin. And that is what is shown in the frequency domain representation, a dedicated peak of spectral amplitude at their corresponding frequencies of the sinusoidal signals. This means for the first signal, a peak at 10 Hz, for the second signal, a peak at 20 Hz, and for the third, a peak at 50 Hz. In the case of the last signal, we see 3 distinct frequencies at 10, 20, and 50 Hz, indicating that the signal consists of 3 distinct frequency components. In this context, it's important to bear in mind that the frequency range that we can evaluate goes from 0 to half of the sampling rate, the so-called Nyquist frequency. For example, if we have a sampling rate of 512 Hz, we will be able to evaluate frequencies only up to the Nyquist frequency, which is from 0 to 256 Hz. Another point worth remembering is the distinction between the term half spectrum, also called two-sided spectrum, versus full spectrum, which is also called one-sided spectrum. Let's use the same 10 Hz sine wave with an amplitude of 10 microvolt. Due to the mathematical expansion of Fourier transform, the half spectrum is basically the spectrum resulting in both the positive and negative frequency values, each with an amplitude that is half of the original signal. The spectrum for the negative frequencies is only a mirror image of the spectrum for the positive frequencies. Therefore, the negative frequency values that are redundant can be folded over to the positive frequency values by computing its full spectrum. What we get is the same frequency component at the same frequency bin with an amplitude that is exactly the same as the amplitude of the original signal. Moreover, there is a theorem called Parseval's theorem, stating that the total energy in the frequency domain is equal to the total energy of the signal in the time domain. This means the resulting power spectrum obtained by computing the full spectrum fulfills this theorem. It's also important to bear in mind that by applying FFT, we are preserving not only the spectral content, but also the energy of the signal. Please note that statistical analysis is not influenced by the computation of half or full energy, as long as the same computation technique is used for all datasets that goes into the statistics. Okay, now that we have covered the theoretical background of FFT, let's move on to its implementation in Analyzer 2. In Analyzer, we offer the discrete version of the Fourier transform. As you may recall from the previous slide, there was an integral running from -infinity to +infinity in the equation of the continuous Fourier transform. Fortunately, we don't have to do this in practice because we collect data within a finite time frame. So we end up having a set of discrete points running from time 0 to the end sample that we are able to measure. Therefore, in order to apply Fourier transform on a discrete set of samples, we have to use the discrete version of the Fourier transform. The Fast Fourier Transform algorithm, which is an algorithm for fast calculation of discrete Fourier transform, is also what's implemented in Analyzer. There are certain assumptions and prerequisites to remember prior to applying FFT. Fourier transform is an adequate tool to analyze stationary signals because the result we obtain from the Fourier transform is easier to interpret if the input signal is stationary as compared to an input signal which is non-stationary. So, stationarity is a keyword in this topic. However, EEG signals are non-stationary by nature. That means the morphology of the signal varies over time. So if the signal changes over time, Fourier transform will not tell us the time information at which the change has occurred. In other words, the time evolution of the frequency pattern is lost because it tells us only about what frequencies are contained in the signal and not at what time. Therefore, it's important to apply FFT to those signals that can be assumed as stationary or quasi-stationary. Quasi-stationary signals in the sense that the spectral properties vary slowly with respect to the carrier frequency or the main frequency so that we can still get meaningful results. So when we apply FFT, we need to first extract portions of data that can be considered as quasi-stationary. Moving on to the prerequisites, the FFT algorithm requires that the number of data points within a segment has to be a power of 2, and it is necessary for the efficiency of the computation. These are some examples showing data points with a power of 2. Please note that these are not meant to be a recommended segment size, but just used to illustrate the definition of power of 2. Now, you might already be asking, what will happen if I don't have a segment that is a power of 2? Well, in this case, the algorithm is programmed in a way to internally expand the length of the segment to the next power of 2 by adding zeros, which is also known as zero padding. So this process will happen automatically internally when the algorithm encounters a data that is not a power of 2. Zero padding in the time domain is equivalent to interpolation in the frequency domain. Therefore, interpolation will take place internally, keeping the energy of the input signal constant. This means that you will only notice the consequence at the later stage when you observe at the frequency resolution. We have discussed that the sampling rate will constrain the range of frequencies that we can evaluate. But in addition to that, the sampling rate also introduces another constraint to the frequency resolution, which is given by the sampling rate divided by the number of data points, n. We will use now 2 examples in order to have a better understanding of these 4 parameters. the sampling rate denoted by SR, the segment length T, the number of data points N, and the frequency resolution delta F. The power of 2 column is where we will decide if the number of data points within a segment is a power of 2 or not. So our first example is an EEG data recorded with a sampling rate of 512 Hz, having a segment length of 2 seconds, which is assumed to be quasi-stationary. And now, if we multiply the sampling rate by the segment length, we will get the number of data points contained within this segment, which is 1024 in this example. Now, let's ask ourselves, is this a power of 2? Yes, as you can see, we can represent 1024 as 2 to the power of 10. So the frequency resolution will be the sampling rate, which is 512, divided by the number of data points, which is 1024. And it results in a maximum frequency resolution of 0.5 Hz. What does this mean? This means if we have a Fourier coefficient at the frequency of 10 Hz, the next Fourier coefficient will be at 10.5 Hz, with a step size or an increment of 0.5 Hz resolution. The graphical display here shows solid colors, but we need to remember that the spectrum consists of discrete values. Now let's take the second example, which is an EEG data recorded with a sampling rate of 1000 Hz. And let's assume that our goal is to investigate the spectrum with a frequency resolution of 1 Hz. We could think now that the good approach will be to define a segment length of 1 second, meaning that they will have 1000 samples. Using the formula, we would divide 1000 Hz by 1000 data points, and we will think that we will get a frequency resolution of 1 Hz. But please be aware here, we will not be able to get a frequency resolution of 1 Hz. Why? Because we have forgotten to ask ourselves if 1000 is a power of 2 or not. And as you can see, it's not a power of 2. So the algorithm is going to perform zero padding in order to get a length that is the next power of 2, which is 1024. This means the length of the segment increases from 1 second to 1.024 second. So instead of a frequency resolution of 1 Hz, we will have a frequency resolution of 0.97 Hz. It might seem to be a fine resolution, but it does not reflect the true maximum resolution. So the important message here is that you may need to adjust either the sampling rate or the segment length prior to applying FFT in order to avoid the need of internal zero padding and also to achieve your desired maximum frequency resolution. Okay. Before we go to Analyzer, let me walk you through the recommended procedure for computing spectral information. By now, you recall that stationarity is the keyword for FFT and why it is important to use stationary or quasi-stationary signal when applying FFT. So when we think of integrating FFT in our EEG analysis pipeline, the most relevant step next to pre-processing your signal is to extract portions of data that can be considered quasi-stationary. This means to perform segmentation. An example will be extracting portions of eyes open or eyes closed task from a resting state paradigm. Usually, these segments vary in length as subjects might keep their eyes closed for 6 seconds in one trial and in another trial for 10 seconds and so on. So the next step will be to apply another segmentation to divide it into equal-sized segments. The aim of applying segmentation for the second time is not only for creating equal-sized segments, but also to adapt the segment length to be a power of 2 in order to get the desired frequency resolution. Moreover, it also helps to gain statistical stability and reliability of results by estimating the stationary part. So finally, we can apply FFT and obtain the spectral information for each segment separately. As you can see in this plot, you can already see the variability of the energy distribution across frequency bands from one segment to another segment. In order to obtain a more reliable pattern of the frequency content across all segments, we can compute the average of the FFT spectrum. This will improve the signal-to-noise ratio by averaging out the residual intertrial variance. You can easily relate the procedure of averaging to an ERP analysis, for example, where you would average across segments to improve the signal-to-noise ratio in order to obtain a reliable ERP component. Okay, now it's almost time to go to Analyzer, and we will be using these steps in the demo. For the demonstration, we are going to use a resting state paradigm where participants were asked to keep their eyes open and closed. And we will demonstrate the already known hypothesis that alpha activity increases when the eyes are closed, which results in a larger spectral power within the alpha range. So let's see that. Okay, let me now open Analyzer. Okay, so this is our raw data, and the data was recorded using 32 channels, including 2 mastoid channels and 4 EOG channels, 2 for the vertical and 2 for the horizontal. And this data was online referenced to the FCZ electrode. So in this paradigm, the participants were asked, as I said, to perform the task of eyes opening and eyes closing 3 times each. And this resulted in 6 blocks. So in order for you to see the 6 blocks, let me squeeze the time span using this magnifier minus button from the toolbar. So basically it's zooming out. Okay, so now we are already seeing the first marker. So here you see the marker called EO start. So we have a dedicated marker to identify the start and end of each block. So EO stands for eyes open. So if I move the bar to this block, it's not enough, so a bit zoom out so that you will be able to see nicely the first block of eyes open condition. You see now EO start defines the beginning of the block and EO stop defines the end of the eyes open condition. Likewise, if I move now the bar to the second block, you can nicely see the eyes closed condition identified by the start, EC start, and the eyes closed condition ending identified by the EC stop marker. Likewise, I will move to the third block, and you see another block of eyes closed condition. Similarly, if I move to the next block, you see another block for eyes open. And the fifth block, you see it's the block for the eyes closed. And the last block, which is the sixth block, is the block for the eyes open. So you see these are the 6 blocks, and each task is repeated 3 times. So eyes closed will have 3 blocks and eyes open will have 3 blocks. So remember this number because we will need it at the end when we perform segmentation. Okay. And I will not go into detail to explain about the pre-processing pipeline, but as you can see here in the history tree, common pre-processing pipelines have already been prepared and applied to this data, like filtering, raw data inspection, and ocular correction using ICA. And this is to remove physiological and non-physiological artifacts. So for our demo today, we can use this last pre-processing node as a starting point for our further analysis. So this data is sampled at 1000 Hertz. So let's check if that is correct. So we go to properties. So you can see here the sampling rate is 1000 Hertz. And as we have discussed before, manipulation of the sampling rate or segment length is quite often a necessary step in order to achieve a desired frequency resolution. And also it helps us to avoid zero padding. So with a sampling rate of 1000 Hertz, it's not that easy to adjust the segment length to make it a power of 2. Of course, unless we create a fractional segment length, for example, a 1.024 second segment to get 1024 data points. But it's not that much necessary to create fractional segments because it has a consequence which leads us to zero padding. So it is preferred to manipulate rather the sampling rate. So let's start adjusting the sampling rate. So how is it done? This is done by calling the transformation change sampling rate. So we will try to select a sampling rate that is a power of 2, and we will choose 512 Hertz. And why is that? Because it is recommended to downsample the data, because if you upsample the data, you have to be aware of aliasing effects. So due to this reason, we have not upsampled the data to the next power of 2, which will be 1024, but instead we have downsampled it to 512 Hertz. Okay, I will use the default spline interpolation, and I will click OK to finish the dialog. Okay, we have now a new node in our history tree, and to keep track of what we have performed, let's rename it and include the new information of the sampling rate, which is 512 Hertz. Okay, the next step is to extract portions of the EEG data where we know that the data can be assumed to be quasi-stationary. This means the duration where the participants were doing the tasks. So to do that, let's call the transformation segmentation. So segmentation can be found under the group segment analysis functions. Okay, since we have dedicated markers indicating the start and end of each block, I'm going to use this fourth option, create new segments limited by start and end markers. Okay, I will go to the next dialog. So here I have the possibility to select the start and end markers. So I will select EO start to define the start of the segment. And from here, I will select EO stop to indicate or to define the end of the segment. Then I will click on next and finish the dialog. So you see here at the status bar, these are the 3 blocks for the eyes open condition. So as I have said in the beginning, 3 blocks for eyes open, 3 blocks for eyes closed. And that is what we get here by extracting segments of eyes open. So to keep track of what we have done, I will include this information so that we will know that we have already finished extracting portions for eyes open. Okay, now comes the point where we want to divide this longer segment into smaller segments to adapt the frequency resolution. So let's say we want to have a frequency resolution of 0.5 Hertz. So let me call again segmentation, but this time I will use the second option, divide dataset in equal size segments. I will click on next. So we know that our sampling rate is 512 Hertz. And in order to get 0.5 Hertz, how many data points do we need? So we would need 1024 data points. So in order to define or create 1024 data points, let's say we defined a segment size of 2 seconds, and as you see here, it results into 1024 data points. Okay, that is all what we need in this dialog. I will click on next and finish the dialog. So you see here at the status bar, we get 90 smaller segments, 2 seconds each. So this means we will now be able to evaluate the spectra with a resolution of 5 Hz. So to keep track again, let me rename that this is a segment of length 2 seconds. Okay, now we are ready to call the FFT transformation. And you can find FFT under the group Frequency and Component Analysis. You see here FFT, I will click on it. And this is the dialog of FFT. The very first group in the FFT dialog is about defining the frequency resolution. And as you can see, by default, Analyzer already detects the maximum resolution that we can achieve with the input data that we have prepared so far. So this shows that we have correctly prepared the data to achieve our desired resolution of 0.5 Hz. So we will stick to this option. But you see also here that there is a second option called Other Resolution, where it allows user-defined resolution. But please be aware that if you are going to change the detected maximum resolution to a new resolution, an interpolation process will take place. Because the data points have to be interpolated to match the new resolution, you will not be able to gain any information about the true spectral content of your input signal. But however, for your display purpose, for example, if you want to obtain a smooth spectrum by changing the maximum resolution, let's say to a very fine resolution of 0.01 or 0.1, then you could use this option. But for quantitative analysis, it is recommended to use the maximum resolution. And if you are still not content with what you get as a maximum resolution, it is advantageous to go back and make the necessary adjustments to the sampling rate or the segment length to achieve your desired resolution. Okay, the second group in the FFT dialog is about the possible output options. Let me briefly go back to the slide and mention the possible use cases of each option. Okay, if your goal is to obtain spectral amplitude at each frequency bin, then you can select the output option voltage, which is basically taking the magnitude of the Fourier coefficients. And if your goal is to compare spectral amplitude distribution between two different signals, and let's say these two signals have different frequency resolution, then you can select the output option voltage density, which normalizes the spectral amplitude by the frequency resolution. This helps in minimizing the amplitude differences arising from different spectral resolutions. Similarly, spectral power can be computed by selecting the power option, which is taking the magnitude squared of the Fourier coefficients. And in order to compute power spectral density, for example, to compare the power distribution between two different signals having different frequency resolution, you can select the power density option, which is normalizing the spectral power by the frequency resolution. But you must be asking by now, how about obtaining the Fourier coefficients? Don't worry, in a later slide, we will walk you through on how to generate these complex values and also provide you with a possible use case for generating them. Now let me go back to Analyzer and continue with the demo. Okay, so for the demo, since we are going to investigate spectral power, we will select the power option, and we will also select the option use full spectrum to obtain a one-sided spectrum. Okay, so the third group is about data windowing, but we have not yet covered this topic. But right after the demo, we will discuss that in detail, the benefit and consequences of windowing. Then it will be clear why we have used here a Hanning window. Okay, here you see a parameter called window length. So by adjusting this window length, the graphical representation will also adapt accordingly and shows you how your input will be suppressed. So, for example, if you put 100%, the left and right sections of the input signal will be highly suppressed, and only high emphasis will be given only to this middle section. And let's say if you put 0%, it is equivalent to using the option no window, as the window resembles the internal default rectangular window. So for now, I will use 10, and it will be clearer next when we discuss about windowing. So for now, this is the only setting that we need to compute the spectral power. But here the last group, which is about normalization, is not applicable for our demo, but we will provide you with a possible use case for using this option when we talk about post-processing. For now, I will press OK to finish the dialog. Okay, so we have now the power spectrum for each segment. And from literature, we know that alpha activity is more pronounced in the posterior region. So let's select a couple of occipital channels. I will select O1, select OZ, and O2. And then I will double click in order to visualize these electrodes only. Let me increase or scale up the amplitude a bit for better visualization. Okay, as you see here in Analyzer, frequency bands have dedicated predefined colors, which you can of course change by going to the view settings. To open the view settings, what you can do is being in this FFT visualization window, you can simply right click and select the option Settings of Grid View. Then navigate to the tab called Bands. You see here Bands, so I will click there. So here you can see Analyzer's default band color, as well as here you see the default frequency range for each band. And our interest, which is the alpha band, has a green color, and it ranges from 7.5 to 12.5 Hertz. So our focus will be within this green area. Okay, I will cancel this to finish the dialog. Now, if you scroll using the next button in your navigation bar and navigate and inspect each segment individually, you can see already the variability of the energy distribution across frequency bins from one segment to another, right? So this is exactly the same mechanism as you would inspect each segment in an ERP or event related studies. So for now, let's rename the node to indicate that we have computed power and used a window length of 10%. This was supposed to be actually equal. Sorry, it was a typo there. Okay. Now, the next step is to average the spectral patterns across all segments in order to extract their common spectral content. So in order to do that, let's call the transformation average, and you will find this transformation under the group segment analysis functions. I'll click on average. We will use all the available segments. So I will stick on using the option use full range. Click OK. And now it's computing the average power spectrum across these 90 segments. Okay, now this is our average power spectrum. Let's look again at the same selection of channels, O1, OZ, and O2. I will increase the amplitude a bit and zoom in using this magnifier glass so that you can clearly see the alpha band. So we see already quite a nice high spectral power in the alpha band. So if we inspect further within this green area of the alpha band, we will now be able to analyze spectral values from 10 frequency bins because of our 0.5 Hertz frequency resolution. Please have a look at the status bar down here where it says POS, that's the position. in order to observe these bins nicely. So if I'm now highlighting at the beginning of the alpha band, so it says now 7.5 Hertz, right? So this is the beginning of the alpha band, which is the default beginning range in Analyzer. And if I move now further, the next bin, it jumps to 8. And if I move further, it jumps to 8.5, one further to 9, 9.5, and so on. So with this step, which means using this 0.5 Hertz step, these 10 spectral values from these bins can be further analyzed. So for now, we have finished computing the averaged power spectrum for our eyes open condition. Yeah, so what is left would be to perform the same pipeline for the eyes closed condition. It means we will repeat the same step, but don't worry, it won't take us long. Thanks to Analyzer's quick and efficient approach of copying analysis steps, we don't have to repeat it manually. So what we need as a start is to extract segment of eyes closed, right? So we go back to the first node of segmentation where we have extracted eyes open conditions, and right click on that node and select edit parameters copy. Okay, I will use the same option for segmentation because I have the start and end dedicated marker. And here we have the possibility to modify the start and end for EC, which is eyes closed. So I will select EC start and here the EC stop. Okay, I will click next and finish the dialog. So as you see, not only the first node was replicated, but also its child nodes are also being created. Now we have our second branch for the eyes closed condition. So in order to avoid confusion, let's rename it to indicate that this is portion of data for EC, and the last one is the average power spectrum for EC or eyes closed. Now what we can do is to compare the spectra of eyes closed to that of the eyes open. And the easiest way to compare two conditions is to create an overlay. Let's open the average power node for eyes open condition. And then to overlay, what you need to do is to click on the average power EC node and drag it or overlay it to this open window. There is already a huge amplitude. Let me decrease it a bit. Okay, so the red line is the envelope of the spectrum for the eyes closed condition, and we can see already a tremendous difference within the alpha range. So if I select only one channel, you can already nicely see the difference between spectral power between eyes closed, which is the red line, to that of the eyes open, which is the this black curve. So you can apply this nice feature of overlay to compare and contrast results between subjects or between conditions. So with this, I will end the demo session. Let me briefly go back to the slides and summarize what we have learned so far. Okay. FFT provides an adequate representation of the EEG data in the frequency domain by revealing the hidden spectral content of the time domain signal. Sampling rate and segment length are the key parameters to obtain a desired frequency resolution. Frequency resolution and window length are essential FFT parameters in order to obtain optimal spectral estimation. FFT transformation can be applied as long as the underlying oscillatory patterns are stationary or quasi-stationary. An example will be performing spectral analysis of the alpha activity during eyes closed or eyes open paradigm, as we have seen in the demo. Now, let's talk about the well-known problem that comes along with FFT, the issue of spectral leakage. With the next two examples, I will try to illustrate what spectral leakage means and a possible scenario when it will occur. So our first test signal is a sine wave with an amplitude of 10 microvolt and a frequency content of 1 Hz sampled at 512 Hz. This means we would expect the result of FFT to show us a peak at the frequency of 1 Hz, right? Let's see if that's the case. So, out of this continuous signal, let's extract a 2-second signal of interest. Within these 2 seconds, we have 1024 data points, which you can get by multiplying 512 by 2. FFT implicitly assumes that the input signal, which is this 2-second signal, repeats itself and thinks that the signal is a never-ending continuous train of sinusoidal waves. So it tries to copy this snippet of signal and appends it before and after. The appended signal looks exactly the same as the original signal. In this case, the signal is said to be periodic, in the sense that there is a continuous or smooth transition at the junctions where the snippet of the signal is appended. Now, before applying FFT, let's first ask ourselves if 1024 data points is a power of 2. Yes, it is a power of 2, as we have seen it previously. Good. Now we can apply FFT and compute its full spectrum. The frequency resolution according to the formula will be 0.5 Hz. This means the frequency bins are spaced 0.5 Hz apart. Since the frequency content of our sine wave was 1 Hz, as expected, we have confirmed with the help of FFT the frequency spectrum to be exactly at 1 Hz and 0 at the adjacent frequencies. In other words, if the input signal has a frequency which is an integer multiple of the frequency resolution, then the entire energy will hit the bullseye at exactly 1 frequency bin, and the remaining frequency bins will have 0 energy. As you can see in our example, 1 is an integer multiple of 0.5, and that proves why we get the exact peak value. Moreover, the amplitude is also preserved. So far, so good, no leakage. So let's check out the second test signal. It's again a sine wave with an amplitude of 10 microvolt, but with a frequency content of 1.25 Hz, which is sampled at 512 Hz. We might expect to get a peak at the frequency of 1.25 Hz, but let's find out if that's the case. In a similar way, let's extract a 2-second signal of interest having 1024 data points. FFT implicitly assumes that the input signal repeats itself. So it tries again to copy this snippet of signal and appends it before and after, as we have seen it before. But now, the appended signal does not look like the original signal. In this case, the signal is said to be non-periodic in the sense that there is a discontinuity or an abrupt transition at the junctions where the snippet of the signal is appended. Let's apply FFT and compute its full spectrum. The frequency resolution according to the formula will be 0.5 Hz. This means the frequency bins are spaced 0.5 Hz apart. However, with this frequency resolution, it is not possible to resolve a peak value at 1.25 Hz. Instead, the nearest adjacent frequency bins are 1 and 1.5 Hz. So, these sharp discontinuities, or the so-called transients in time domain, produce a broadband frequency content. Therefore, the frequency spectrum cannot represent 1.25 Hz, and its energy gets leaked or spread over across other frequency bins, leading to a phenomenon called spectral leakage. In other words, if the input signal has a frequency which is not an integer multiple of the frequency resolution, then the entire energy will not be depicted in one frequency bin, but rather spread over across other frequency bins. As you can see in our example, 1.25 is not an integer multiple of 0.5, and that proves why we don't get the exact peak value. Moreover, the amplitude is also distorted due to leakage. Okay, I hope now we know what spectral leakage means and how it occurs. In reality, EEG oscillations have non-periodic characteristic, and its frequency content does not necessarily be an exact integer multiple of our desired frequency resolution. This means we know that we will be facing with the challenge of spectral leakage. If that is the case, how can we handle it? The remedy is to eliminate or at least reduce the sharp discontinuities by smoothing them out. And this is done by a technique called windowing. This means prior to applying FFT, multiply the input signal by a window function, for example, using the popular Han window. As you might recall, most window functions have a bell-shaped curve that start and end at a value of 0. And this helps in attenuating or smoothing the sharp transients at the borders. When the windowed snippet of the signal is copied and appended, the appended signal will now have a smooth transition and no more abrupt transition. Therefore, the leakage will be reduced and confined to a narrow frequency range, rather than affecting the entire frequency spectrum. Now, one might think, instead of being affected by spectral leakage, why not to extract a signal of interest that results in an integer multiple of the frequency resolution? But unfortunately, it is not possible to know the frequency content of your signal of interest in order to match it with the frequency resolution. Had it been possible, we wouldn't be performing frequency analysis, right? So, is it really possible to find the actual frequency even when spectral leakage occurs? Yes, you can achieve that by having a finer frequency resolution. To illustrate this with an example, let's use the same signal and this time apply FFT on the entire 6 seconds. The longer the signal duration, the finer the frequency resolution gets according to the formula. Care should be taken though while prolonging the duration of the signal of interest, because the longer the signal gets, the less stationary it becomes. So we should keep in mind the quasi-stationarity concept that we have discussed. In this example, since it's a pure sine wave, it will still be stationary. So in these 6 seconds, we have 3072 data points. But as you might have already noticed, it's not a power of 2. So internally, zero padding will be performed and we get 4096 points, resulting in a resolution of 0.125, which is a very fine resolution. Now, with this resolution, it is possible to hit the bull's eye at exactly 1.25 Hz, which is the frequency content of our input sine wave. But the full energy is not confined to a single frequency beam. Instead, it propagates or leaks to the entire frequency spectrum, as you can see here with the ripples. And this is the effect of zero padding, resembling like spectral leakage, which also distorts the amplitude of the spectrum. Because after zero padding, we don't get any more a pure sine wave. If we now apply a Hanning window, the windowed frequency spectrum shows how the propagated energy is now nicely confined to a narrow frequency band. In the FFT dialog, you have the possibility to adjust by how much you want to attenuate the signal. For example, here we have used 25%, which means 12.5% of the signal is attenuated from the left and right side prior to applying FFT. Good that we have resolved the leakage issue. However, we are still left with one final issue, and that is not only the energy of the signal is reduced, but also the amplitude has been even more reduced due to windowing. Generally, correction factors can be used to compensate the variation caused by windowing. So the important message here is that while thinking about frequency domain representation, it is necessary to be aware of spectral leakage. And to overcome spectral leakage, it is recommended to apply windowing. Let me now summarize the whole story about spectral leakage. Spectral leakage is the phenomenon where the energy of the signal is spread across adjacent frequency bands due to sharp discontinuities at the borders, because sharp transients in time domain result in a broadband frequency content. The consequence of spectral leakage is that it makes it difficult to quantify the spectral content of the input signal, because it alters the amplitude and energy of the signal. Spectral leakage cannot be fully eliminated, but can be reduced with the help of windowing. Although windowing helps reduce leakage, it's also important to be aware that not only the energy, but also the amplitude of the data will be altered. Okay, so after successful decomposition of our EEG signal into frequency domain, the next question is how to extract quantitative measures for further statistical analysis. Without going in further detail, I will briefly point out the measures that can be extracted from the spectral values and the ways to extract them. So if you intend to export the output values for each frequency bin, you can use the generic data export module in the same way as you might have already used it to export other data. But if you intend to export measures like the area information or the mean activity or the summation of spectral values around the strongest frequency content, you can use the area information export. But one side note here is that the area information export module is designed to work on average data. So in case you intend to export same measures from non-average data, you can use the solution called FFT band export. This solution is part of our official solutions package and can be downloaded from our website. Another measure that can be extracted from the spectral values is the phase of the oscillations. The FFT module does not directly provide you with the phase output, but it enables you to compute the complex Fourier coefficients, which are used for the computation of the phase. So the recommended setting to compute the complex coefficients is to select the voltage output option, along with the option produce complex output without the application of any window, and that is to preserve the original phase. So this is how you generate the Fourier coefficients. Once you have generated the FFT node with these settings, for visualization purpose, the plot will show you the absolute value of the complex values, meaning the spectral amplitude. But if you export the data stored in that node using generic data export, you will get the complex values, that is the corresponding real and imaginary values, or the so-called Fourier coefficients for each frequency bin. This example shows you how to interpret the exported file. For each electrode, you will have two columns, one for the real and another one for the imaginary part. And the row represents the frequency bins starting from 0 with an increment of your frequency resolution. In this example, each row increments by 0.5 because we have a frequency resolution of 0.5 Hz. You can then use this information and compute the phase in Excel or any other third-party softwares. But we do also offer you a possibility to stay within Analyzer, and that is, for example, by using the MATLAB transformation, as long as you have the license for the MATLAB software. Within the MATLAB transformation, you can make use of the ATAN2 and ATAN2D functions to compute phase information either in radians or in degrees. So this is really a brief information, but if you intend to analyze phase information and need further assistance, please feel free to contact us or send us an email via our email account support@brainproducts.com. Okay, in addition to the computation of absolute power, it is sometimes desired to compute relative measures. such as the change of spectral power in comparison to the power within a specific frequency band. An example would be to compare different frequency band activities to that of the alpha activity, or there might be a need to express the percentage contribution of each frequency band to the total power. Here, an example would be to compare spectral powers between channels or subjects. The computation is done by dividing the absolute power value of each frequency bin within a segment by the sum of absolute power within the specified frequency range and multiplied by 100. So if your goal is to compute normalized power, then the recommended FFT setting is to compute the full absolute power spectrum by selecting the power option, along with the option Use Full Spectrum, and then enable the Normalized Segments option under the Segment Normalization section and insert the desired frequency range that will be used to normalize each of the frequency bins. Okay, before I provide you with the take-home messages, let me try to address some of the open questions. In case you have not yet sent your questions, please feel free to send them via the chat window in the questions pane of your control center. We will try to cover most of your questions. Okay, I have already received the first question. Can I export spectral values generated by the transient FFT? Yeah, that's a good question. Let me first use this opportunity to inform our other audience what is meant by transient FFT. There are in fact two ways to access FFT in Analyzer. Let me go back to Analyzer to show you that. So one option to access FFT is from the transformations ribbon menu, as we have seen it in the demo. And another option will be to access it via the transient mode. What it means is you just need to activate your time domain data and then select an interval of your interest like this using your mouse. And automatically when you release your mouse, a context menu will appear, which lets you to select FFT. So now if you click on it, a dockable window, which is shown here on the right, and also known as the transient FFT view, is generated. And it contains the spectral content for this selected portion of data. So for better visualization, let me highlight only one channel. Double click on it. I will increase a bit the amplitude so that you can see it clearly. So this feature enables you to inspect your EEG data. So if I now drag or move this highlighted section of the EEG like this, as you can see on the right, the result is automatically updated. And you see the spectral amplitude for the new position. So this is really a nice feature to inspect the EEG on the fly. So as you can see, without even generating an FFT node, you can already tell that there is a high alpha spectral content for this data. Not only this, but you can also this feature to inspect some artifacts. For example, let's say the presence of line noise in your EEG data. And in case you have a line noise in your data, this spectral amplitude will show you a very high peak at 50 Hertz. And also at its harmonics like 100 Hertz or 150 Hertz and so on. So this means this feature can only be used for visualization purpose. So to answer the question, it is not possible to export spectral values from this view because it's only a temporary display and no values are stored. So exporting values can only be done by creating the average FFT node or by creating not even average, but can also be non-averaged FFT node, like we have done in the demo part. Okay, I hope that answered your question. Okay, still checking for incoming questions. When do we use a sliding window overlapping segments in segmenting before FFT? That is an interesting question. So this kind of technique or creating overlapping segments is also known or mainly used in the Welsh method, and it will help you to, for example, instead of, because when you window your data, the right and the left side of your portion of data will be dropped. And in order to avoid loss of data, when you overlap your segments, you can still capture or retain these portions of data. So for this reason, a sliding window is of advantage. And in order to do that in Analyzer, for example, you can use the overlap segments option, and then you can select a desired segment length or second, where you can also see here its corresponding data points. And then if you know how many points you want to reserve, like not to lose it by the effect of windowing, then you can create an overlapping segment like this. So the need for sliding window is basically to preserve loss of data. I hope that answers your question. Okay. I'm still reading on questions. Would you advise against performing FFT on segments recorded in an ERP experiment? That's also a good question. So basically, like I have mentioned earlier, in FFT, you would not gain any time information. So in common ERP experiments, time dynamics or the dynamics of the frequency content is sometimes of desire. So in that case, it might not suffice, or it might not be feasible for your goal. But in order to obtain what kind of frequency is existing in your raw data, you can still use FFT. But this might not answer your research question. So, but as long as you don't want to observe the time dynamics, you can still perform your FFT. But basically in ERP analysis, you would like to compare with respect to the pre-stimulus period. So like synchronization or desynchronization, and that could be better realized or analyzed using either wavelets, which is the time frequency analysis, or using the ERS-ERD technique. But as I said, just to observe or to obtain the frequency content of your signal, you can make use of FFT. Okay, there is another question. Is it always necessary to segment data and average it, or does it only make sense when comparing segments of different time length? That's a good question. Okay, so it is for sure necessary not only for comparing segments or not for making it equal size segments, but by subsegmenting your data, what you will achieve or what you will assume is that this portion of data is stationary or quasi-stationary. And this assumption is quite relevant for FFT, because in order to interpret your result at the end, this criterion should be fulfilled. So that is why it is very necessary first to segment your data and then apply FFT on it, and then at the end average. Of course, after performing FFT, because if you already average and apply FFT, you will already lose the frequency content of your signal. By averaging, you will cancel them out and you will not get the true spectral content. So I would advise to first segment the data to have or to fulfill this quasi-stationarity requirement for better interpretation of your result, and then average it. Okay, I hope that answers your question. I will move on to the next question. How do I know what resolution is appropriate? That's also a good question. Selection of frequency resolution basically depends on how fine or coarse you would like to analyze the spectral content of your signal. This means, for example, if you'd like to resolve frequency differences of, let's say, 1 Hertz and not less, then it is, in this case, the appropriate choice of frequency resolution will be 1 Hertz. But if you think this is a very coarse resolution for your research goal and would like to make it more finer, then you would go for a less resolution. So it really depends on what you would like to achieve. So as a starting point, it might be helpful to check for literatures in your research field to know the adequate frequency resolution. Okay, I hope that answered your question. Okay, I'm looking for other questions. Can you explain one more time what's the difference between power and power density export options? Okay, sure. So if you compute power, so this is the pure, so basically the difference between power and power density is, in power density, you normalize the power that you have computed with your frequency resolution. So for example, if you have 2 conditions that you would like to analyze, but these 2 conditions have a different frequency resolution. Okay, so in order to take out the effect of this difference between having different frequency resolutions, you would compute power density. So that is basically the difference and benefit of computing power density with respect to power. So again, to repeat, power density takes out the effect of 2 conditions. If you are comparing conditions, takes out the effect of differences in frequency resolutions, because it normalizes the computed power in the same way as you compute normal power, and then it just normalizes it by the frequency resolution. I hope that is that makes it clear now. Okay, I'm still checking for questions. Do you have a recommendation for the length of segments to fulfill the assumption of quasi-stationarity? That's a good question. Actually, there is no standard or golden rule that says either 1 second or 2 seconds will fulfill quasi-stationary criteria. It's really depends what kind of task the subject has performed. So if you think that the specific task that you would like to analyze is stable within 1 second, then that second can be considered or is feasible to say this duration is quasi-stationary. Or if you think within 2 seconds I still have a very stable signal, then that 2 seconds for you, so for your task or for a paradigm, can be considered as quasi-stationary. So like I said, there is no really standard rule, but so if you go more higher, you make fine resolution, and if you go if you decrease the length, then you have a coarse frequency resolution. So there's always a trade-off between these two things. So I would recommend to have a look or check based on your paradigm or task. I hope that answered your question. So, okay, let's look at the time. I think I will now pause receiving further questions. So due to time constraints, I hope we have covered most of your questions, but if we are not able to address them all, please feel free to send your questions to our email account via support@brainproducts.com. Let me go back to the slides and give you some concluding remarks to recap what we have discussed in today's webinar. The important take-home messages are the following. We have seen that brain dynamics are characterized by oscillations in different frequency bands, which reflect cognitive processes. We know that FFT transformation can be used as long as the underlying oscillatory patterns are stationary or quasi-stationary, as we have seen in our example of the resting state paradigm. So we need to pay attention to the signal that we are analyzing, in the sense that it shouldn't be a transient signal. FFT maps time domain signals to frequency domain representation, meaning it tells us the frequency content of a signal contained in the total period of observation. After spectral decomposition, we have seen that using the export modules in Analyzer, it is possible to extract desired spectral features for further statistical analysis. Although FFT is very useful and can give already meaningful information about the spectral content of the EEG signal, it is also important to be aware of the limitation of this method. So, in cases where FFT is not the appropriate methodology for your research goal, for example, in the case of an event-related paradigm, which was one of the questions from our open question session, I guess, so you may need to consider other spectral decomposition algorithms like wavelets, which allows you to analyze the time evolution of the frequency pattern by performing the so-called time frequency analysis. And if you are interested to know more about wavelets, I would like to invite you to check the wavelets chapter in the Analyzer user manual. So are you still interested in further details? You will find detailed information about the FFT module, as well as very useful theoretical concepts via the Analyzer user manual in its dedicated chapter. And in order to have more information about export options, check out this very useful press release article, which will give you a quick grasp about the different export options that Analyzer offers. The link can also be found in today's handout. For further readings, we would also recommend some textbooks where you can get quite a nice introduction on spectral analysis and in general EEG signal processing methods. The books by Cohen, Handy, and Michel are great to learn more about EEG processing methods. And of course, a good starting point is always to check for publications related to your field of research. Okay, with that, I would like to thank you all for joining today's webinar, and we appreciate your active participation. You will receive a follow-up email with a link to the PDF slides and a video recording of the webinar. You can also visit our Brain Products webinar channel via the following link, where you can rewatch our past webinars. Today's webinar will also be available latest on Friday. If you have any questions about the content of this webinar or other topics around Analyzer, please contact us via support@brainproducts.com. On behalf of the whole Brain Products family, I wish you all good luck with your further analysis and happy spectral decomposition. Have a good time. Bye-bye.